Hello, it's Keith here, and this is lesson 78 of the platform-specific series of my Z80 assembly programming tutorials. Today we're looking at the MSX1 and we're looking at what I call Mintile. Now Mintile is a multi-platform tile map solution. It's very basic, minimal tile it stands for, and it's designed to provide a tile map and also some simulated sprites which can move horizontally and vertically and also X-flip. So we've got our sprites here, and if I press the fire button, my character will flip around showing the X-flip off, and you can see that there is some scrolling going on. Now, a couple of things it's important to point out. The sprites are simulated. They're not being done with the hardware sprites. That's because it allows us unlimited size on various systems. This was designed as a multi-platform solution, and these characters are too big for the MSX's tile sprites. And these characters are too big for the MSX sprite capabilities, so by using the tile map we don't really have that problem. Now the other important thing to notice is we're actually using the bitmap mode on the MSX1 today. While it's arguably a tile map, we're using the mode that splits the screen into 3 sections and uses 3 different pattern data sets for those areas. So we're effectively treating the screen as a bitmap screen. Again, the reason for this is it increases the flexibility. If we'd used the tilemap solution, we would have only had 256 possible patterns for the entire screen and also the characters. But Mintile is capable of more than that on a bitmap system, and so the bitmap system seems more sensible. It does, however, on systems like the Master System, use the true tilemap solution. So there we go. So that's what we're going to be looking at today. Let's go over to our code and let's take a peek at what we've got. Okay, so here is the code, and the one we're looking at today is MSX1 Mintile. That's the file we're looking at. Now, this is going to be running from ROM today. In my more modern solutions and my examples, I'm tending to treat the system as a cartridge-based system because it's more limited, and so it means we've got more portability. If we treat the entire system as having RAM, that allows us to do things like self-modifying code, but if we can't do self-modifying code, that means our code is unusable. So by treating it as a cartridge system, which in a lot of cases the MSX1 will be, we've got a more limited system, and that gives us a better code that will be more reusable. So that's what we've got. Now we're using the mode which I believe is referred to as Graphics G2. This is a graphics based mode, but it uses 3 256 tile areas, splitting the screen into thirds, and these thirds all have different patterns, and that means we can have the entire screen with different pixels on every different changeable pixels in every area. So that's what we're using here. Now we need to initialize the screen with the correct settings, and these are the settings we're using here. I think these are the original settings for the regular mode, which doesn't have that 3 sections, which, as I say, this is a bitmap based example, so not appropriate there. And we're transferring the data here so that we've got the VDP set up correctly. Now what we're going to do next is basically we're going to initialize the screen here. What we need to do is we need to set the 3 sections to point to, from the top left corner is going to be tile 0, and the last tile in each third is going to be 255. So we're setting up the screen to show all of the patterns in consecutive order, and then from that point all we need to do is change the patterns to change what's on the screen. That's what we're going to be doing. So what we're doing here is we're selecting the tile map data here, and then what we're going to do is we're going to write values from 0 to 255 from the accumulator here, and we're going to do that 3 times for the 3 thirds. So that's what we're doing there. That is setting up the screen. Now we're going to come back later to the flip LUT. That's for the X-flip function. We'll discuss that later on. And what we're not going to discuss is the code here, which is just a basic example, running the routines that actually draw the tile map and the sprites to the screen. If you want to know how they work, please see the multi-platform series of Mintile, because most of the code is reused on all of the systems, and that's the point of this. It's a multi-platform example, not just on the MSX, not just on the Z80, it's on all of these systems, and so we can treat them in the same kind of way. Okay, so how does Mintile actually work? Well, whether it's drawing the tile map or a sprite, it always works in the same way. Even the sprites are actually miniature tile maps. They're just small tile maps, and what it does is it breaks down the tile map area into individual strips, and it draws them one at a time. Now most of the code is multi-platform, but that strip code is platform specific, and so that's what we've got here. We've got a piece of code, the job of which is to draw a strip to the screen. So here's this do strip, and this will draw a single horizontal strip to the screen. Okay, how does it do it? Well, the first thing it does is that we actually use the stack to quickly read data. So we're backing up the true stack to SP restore, which is just a 2-byte entry in our memory somewhere. And then what we're going to do is we're going to select the VRAM destination. Now this will be in H and L at this point, and so we're selecting the VRAM destination, and that 40 there is to specify writing. Now in the case of the tile map, the entire tile map, then basically we are just writing to the top left corner, and that will be pattern at memory address 0 in VRAM. In the case of the sprites though, we need to calculate the correct destination, and we have a get screen pos function here which will do that for us. Now we're working in entire tiles, we can't move half tiles or anything, and so basically what we're doing is we're converting the x and y coordinate into a tile number here. Now the x and y coordinates are in logical units. One logical unit is 2 pixels. I use that on a lot of my tutorials now. It's very convenient for 8-bit systems. So here we're calculating the VRAM destination based on that. Now the one thing to bear in mind is that when we draw bitmap data to the screen, the VRAM is laid out in such a way that byte 0 would be here, byte 1 would be a line down, byte 2 would be a line down all the way down to byte 7, and then byte 8 would jump back up to the next tile across. That's why we've got those bit shifts there to the x coordinate, and we'll see that in the do strip code as well. Okay, so we've selected our VRAM destination here. We're then loading in a tile number from the tile data. The tile map is in the shadow BC here when we run this routine. And so what we're going to do then is basically we're going to firstly check and see if that tile number is tile 0. If it's tile 0, we don't draw it to the screen. It's transparent if it's a sprite. And if we're drawing the tile map, then this is an unused tile. The tile map is actually a cache of changes, and so we write those back to 0 after we've drawn to the screen. This means that next time if we draw the tile map to the screen, if nothing's changed again, it's very quick indeed and saves a lot of time. So it's actually a change map in that case. So what we're doing here is we're checking if that's an empty tile. If it's not, what we're next doing is checking if the tile clear parameter is set. Now this was done with self-modifying code on most systems, but we could be running from ROM here, and that's not the case. Now if we are to clear the tile, then we're doing that cache and we're writing a 0 back into the tile map. But if we are drawing a sprite, we don't want to do that, and so in that case the tile clear will be set to 0, otherwise it will be set to 1, and in that case we would just skip over to here. Now what we're going to do next is we're going to calculate the source bitmap data, the pattern data of the tile we want to draw to the screen. So basically what we're doing here is we're multiplying the tile number by 16. Why 16? Well, we've got 8 bytes of bitmap data and 8 bytes of color data. The MSX1 actually has surprisingly good color. So we've got 16 bytes of data, 8 bytes color, 8 bytes of pattern, 8 bytes of bitmap data. So we're calculating that there, and we're adding the DE source, which when we run this routine will point to the memory address within the ROM cartridge, or RAM for that matter, of the pattern data that we want to use and draw to the screen. Okay, so now what we're going to do basically is we're going to read in 2 bytes of our pattern data, because we've now transferred that to the stack pointer. We're using stack misuse to read. We're popping DE, and then we're going to out those to C, which is the VDP data port. Now there is a bit of a limitation here, maybe we could say. I was using pop DE because it's fast. However, it's too fast, and the VDP on the MSX1 it cannot cope with the data being fed to it at this speed. So you'll see here there's a lot of no operations here, and this is the absolute minimum I think that I was able to do and get the data to consistently appear on the screen. A note point though is if you're using the MSX2 in MSX1 graphics mode, you can actually remove these no-ops. The MSX2 graphics VDP is faster and doesn't need them. There is, however, a MSX2 version of this example coming later on that has better graphics. But as I say, you might want to use the more limited graphics on your MSX2 for some reason, in which case, as I say, these NOPs are not needed. And one option, of course, could be you have 2 versions of this routine and you have a game that works on the MSX1 with slower graphics and MSX2 with the same kind of graphics but at higher speed, because you no longer need these delays. So anyway, this is transferring the 8 lines of the tile pattern to the screen. Now once we've done that, we are then basically transferring our memory address to the color data equivalent. Now the ORing in of 40 there was to mark that we are writing to the VRAM, However, the 60 here is 40 plus 20, and that's because the memory address 2000 onwards is the color data equivalent to the bitmap data, and so we are shifting to the equivalent pattern color data to the pattern bitmap data that we just wrote, and then we're just simply doing the same job again, writing the next 8 bytes, and our source pattern data has been configured for those to be the colors. We're then writing those to the screen for the matching tile. Now we've now drawn the color data and the bitmap data to the screen, so now what we want to do is we want to move along one to the next pattern that we might want to draw, and so that's what we're doing here, adding 8 to our VRAM destination and decreasing IYL, which is our count of tiles, and if there's more to do we simply draw the next one. We will select the VRAM address and we will then draw that next tile, and we keep repeating in that form until we're done. Okay, so that's what we're doing there. The empty tile routine is simply just skipping over a tile. That's if the tile doesn't need to be drawn to the screen, as I say, in the case that the tile is 0. And that's how we're drawing our unflipped tiles to the screen, the patterns to the screen. So that's the unflipped. What about the X-flipped? How do we do that? And that's another reason why we're using bitmap mode rather than tile mode here, because how would we do those X-flips in tile mode? Well, it's a difficult question. Now, the way I'm doing the X-flipping is basically via a lookup table. What I've done is I've defined a 256-byte block of memory here at memory address C000, and that is our lookup table. And what we're going to do is we're going to pre-calculate the equivalent flipped version of any byte that we might come across in our bitmap data. We don't need to flip the color data because that's 1 color per line anyway, but we just need to X-flip that bitmap data. So we're loading HL here with the address of our lookup table. We're then loading the accumulator with L, and that's the byte that we want to flip. We're then flipping all of the bits. We're basically shifting them right out the accumulator and left into the B register here, which is effectively flipping them. We're repeating until L has reached 0, gone all the way from 0 to 255 and back again. And what we've now done is we've calculated all of the equivalent flipped bytes for the source byte that was passed in, and it was passed in by the low byte of the HL pair. What does that mean? Well, when it comes to flipping a sprite, we basically have a routine called do strip reverse, and so we have to flip our entire sprite in one go. We can't flip an individual tile. On this version, Max Tile will do that. That's the more advanced version I'm working on, so that will allow for flipping individual tiles. This one only flips in entire sprites. Okay, so what we're going to do, well, we mostly do the same thing, but one thing we do is we load BC with the address of the flip lookup table. Now, we calculate our source pattern data the same as before because it's that same pattern data we're going to use. However, this time when we load in a byte from our source pattern data, we load it into C. Now, B is still pointing to the top byte of the flip lookup table. And now what we do is we just simply read in a byte from that lookup table, and because we calculated it using the low byte as the source data and then writing the destination flipped equivalent, we can load in a byte from BC now, and that will be the flipped equivalent of the value that we've got in C, the E we read in. And so we simply out that to the screen, and that's the flipped version. We then just do the same for the D byte that we popped out and write that, load in the flipped equivalent, write that to the screen, and we just do the same for all of the remaining bytes of the bitmap data. Once we've done the bitmap data, we simply do the color data. However, that is identical because, as I say, it's 1 color per line, nothing to X flip. We'd have to Y flip it, but nothing to X flip it. So that's all exactly the same. That's how we're flipping that data and getting it to the screen. So there we go. I mean, as always, you can go to my website and download the source code, the build scripts, and all of that kind of fun stuff. And as I always say, you're welcome to use any part of this code in any way you can. The bitmap data was created with my Sprite editor. I've mentioned it before. It's what I use it every time in my tutorials. If I need graphics, they came out of Sprite editor, so it can create the tile color information that you need for today's example if you want to have a go with that. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.